I say I just saw the comment from Simon on this and the very good question of what happens if I have several responses and so forth. But I mean, the point of this case is, of course, you have something where you thought only a few of those factors or of these effects should be actually active, but you find that quite a lot of them are actually active, and you didn't do enough runs to really be able to be sure just from this experiment. And I really love the way that you solved this, or say the method that you just explained, Victor. So I just wanted to jump in and say, like, okay, yes, this is of course a very intricate way of finding out what could be the right selection. If you are ending up with something which says like, oh yeah, a lot of these things are actually active, and actually there might be more than what we can learn from this current design. And I would ask you Victoria, or say anyone else who's in this forum, how would you feel about going in such a case where you go like, okay, I now have see too many effects to be confident if the DSD actually gave me the right ones. How would you see it to go then like, okay, so let's maybe based on what the DSD found as effects, create a new design, or say augment the DSD to a full say actually fit that model, and see what the final solution would be.
Yeah, absolutely. Just I totally agree, and sorry, I didn't saw the chat during the presentation, so I just see some comments and so on. Winfried, you're totally right. Meaning, here, I mean, first, I totally agree also with Simon saying it's a bit overkill. I mean, completely. When I see some topics here in the jump community, I like to go deep and see what is, let's say, the limit of what we can do. So here it's clearly overkill, but it's a nice, let's say, it's a nice exercise to see, okay, should I trust this model or not? So here the question is more about being, let's say, confident in the effect detected, but we have to remind ourselves that even if it's a definitive screening design, it's not definitive, meaning we have identified some interesting effects, but as Winfried is mentioning, we need to do some validation run, and if we have detected some interaction and quadratic effect, it's best to augment the design with this assuming this model in order to check if it still makes sense, if it's still confirmed by the new runs, or if we need to change our minds and investigate other models. But here it's not the end of the reflection, let's say. It's not, okay, we have found our model and we are done and everything is great and let's conclude. It's just, okay, we are more confident with the model we think may be appropriate for the use case. But as always in DOE, because you have low size data set, very, let's say, information rich, but low size data set, you always need some validation run or to augment your design in order to be sure about the conclusion you will share with the people.
Simon?
Thank you. But the outcome was now after doing this, what's it called? It's big ranking and raster plot that you can trust the definitive screening design platform initially. Is it always the case? Let's say you have a definitive screening design with 26 factors and no, 26, with 6 factors, and all 6 are luckily significant or show an effect, then can I trust Definitive Screening Design platform to make, for example, my optimization design, or do I have to run parallel a lot of models and verify just by remodeling and selecting of the most promising models? Because that would be really, in a practical way, an overkill. Of course, it's really nice, but yeah, I would kill all my deadlines with that.
So
the question is, can you trust the Definitive Screening Design platform?
I would say in general, yes, because the way it was, I mean, you can look at the jump help section. It's quite interesting to look at the explanation on how it is created and how the modeling is done, because it's very clever. So in general, yes, if I do a DSD, I would use the FitDSD platform because it's let's say the way to go. But that doesn't mean you blindly follow what the platform is telling you. And it's quite funny that you are asking this question, because here in this scenario, I mean, it's a perfect scenario. You have a low error and low, let's say, uncertainty in the measurement, it seems, from the data we have. But Frank Derrick, I think he's also in the chat today, so he can talk about this use case. He also used DSD some time ago. He used the FitDSD, and in fact, with the basic settings of the platform, he was not able to find, let's say, I wouldn't say a correct model, but an appropriate model. And it was due to the fact that he had a lot more error in the measurement of the response. So basically, depending on the signal on noise ratio that you have in your experiments, FitDSD can identify effect quite precisely or not. And if you have, let's say, some kind of low signal on noise ratio, it might be a lot more complex to fit models, and you will probably need to use several platforms in order to be confident about the term entered in your model. And for example, in this example of the use case of Frank, I think we used a lot of different platforms, but the one that was quite successful was the fit to level screening. So you know that there is no unique solution. In case of doubt, always try different platforms to see if the model agree or disagree and on which terms. But yeah.
And I would also add, if you have some insights, because in this case, of course, we just see factors. We don't know what these factors are. So if you will have in-depth knowledge of which factors you included, and then you can also know, like, okay, yeah, is this actually, makes this sense? Because that's at the end of the day, of course, the point that you want to achieve is that it makes sense to those people that you actually kind of trying to support with such a DSD. And if you're not able to actually reduce the number of terms that you would need to explain the variation in your data, yeah, then maybe one needs to really think about, okay, do we actually need to go the step further and now increase to a more descriptive model instead of a exploratory model like the definitive screening.
Yeah, we have a question from Varun. Varun, can you unmute and then ask your question, please?
Yeah. Sorry, I think the whole idea. Can you hear me?
Yeah, we can.
Okay. Yeah, I think the whole idea of DSD was, if I understood correctly, that if you have large number of factors, then it helps you to screen down to limited factors. So let's say if I have 20 factors, then I think the whole idea of running and finding, the best model would be not so easy and straightforward. The way you're showing might help, but can you add your comments, or based on your experience, what should I do when I have about 20 factors?
Any take on this? So what if the number of factors is, say, 20 and above, or the number of factors is higher? What would be the typical approach be?
Yeah, Victor?
Yeah, I would say the number of factors is often not a big problem, let's say, when you run DOE, because I would say the higher the number of factor, the less probable an effect or a factor will be significant on the response. Meaning, I mean, unless you have very specific or complex settings or environment. But if you are doing, for example, a DSD with 20 factors, I have hard times to figure out that the 20 factors will all have a big effect on the response. I think perhaps half of it or even less will be very active on the response. So that's why, I think this is why the definitive screening design is very effective in such a scenario. Meaning, if you have a high number of factors, DSD helps you not only to figure out what are the most important active main effects, but also to go a little bit deeper and look at interaction and quadratic effects. You're right that definitive screening design are great for high number of factors. The big difference between DSD and other screening design is also that you have this kind of middle levels in your continuous factors, which are not present by default with classical screening design. And these middle levels helps you to assess if a factor may have a curvature, if you have a curvature effect from your factor on the response. And this can avoid situation where you filter out a factor from your screening scenario, because you see that between the low and high level, it seems to have no influence on the response. But in fact, if you had a middle level, maybe you will have this kind of profile where you see that the middle level has a lower value for the response or higher value on the response. So DSD helps to avoid filtering out effect only based on linear main effect or interaction effect.
Yeah, I mean, sorry, I was not maybe clear, because typically in my case, I have 5 to 6 responses to, so when I model each and every response separately, then I combine all these models to co-optimize the whole thing, because I want to achieve certain settings for one response and maybe certain, want to minimize maybe another response and match the target for another response. It's kind of a co-optimization. So basically, it leads to a full-blown model where some of the factors are important to optimize certain response, but not the other. But I think that whole thing, what you showed, will be helpful. But I specifically want to understand why should I use different models if I can just use stepwise and go and have the forward search and BIC or AICC. It just gives only one model, right? But the reason I still didn't understand why I need to check all these models.
Okay.
Anybody have any take on this? Have you come across this kind of scenario? Yes, Simon?
I just wanted to comment on another point Victor mentioned before.
Okay, so maybe we answer Baron's question. I think, Victor, you were ready to answer, and then Simon, and I don't know if Frank, you also wanted to say something.
Yeah, but well, for the different responses, are you sure that for the model is the same for all responses? If you are sure the model is equal for all responses, okay, but you're not sure that the model will be okay for all these responses. What I do mostly when I have several responses, I check if there's collinearity. Maybe you can do first component factor analysis. So you can reduce the number of responses, and then see if, of course, some responses are correlated. The model will be the same, but if there is no correlation, I think the model can be different. So I am a little bit reluctant to make a model general for all responses.
No, Frank, let me clarify. So responses I cannot remove because that's something I want to optimize, right? But I don't have same model for every response. Every response has different model.
Yeah. Yeah, then of course, yeah. But the DSD is, yeah, I think we are here discussing about the quality of the DSD, right? So maybe for all your response you have, the number of active factors can be different. Sometimes maybe for one you need 3 factors, the other one can be 5, the other one can be 4, 6. Okay? That means that when you have only 3 active effects, I think your DSD project in a response surface model. Very easy. Once you have more than 3 active factors, then you need to be careful because your like Victor already said, you need to you have to check the design evaluation platform to see which interactions are correlated, because in the DSD is the fact that you have the main estimation, the estimation of main effects are pure, are not correlated. The ones for the quadratic effects, a little bit, but nearly pure, but you have a lot of collinearity between your interaction effects. That's a fact. And then I think the first thing you do in a DSD is check very carefully the color table or the correlation color table, and check what interactions are correlated. Because when you have more than 3 active factors, it will be important, because then if you detect some when the FET DSD platform gives you the proposal of your interactions, they may be correlated with other interactions. And then you need to augment your DSD the way that you have to de-alias your correlated interaction effects. That's what the case we have here. We have 5 active effects. I think maybe, Victor, can you show us how you make this correlation table? Is it possible to show us that you have already, maybe we already discussed the design evaluation table of your this DSD?
Yes, Bill.
Yeah.
Yeah. So
yeah. Go ahead.
I'll talk for a couple minutes, but a few things that I think we missed in the way we went through the analysis, which a couple of you have already pointed out. First thing is we have no practical context or subject matter knowledge or domain knowledge of what was going on in this experiment. So the factors are meaningless to us. The response variable is, we don't even know whether we're trying to maximize, minimize. We don't know practical significance, how big of a change matters, and all of that needs to be determined before we do any statistical analysis whatsoever. So we're missing quite a huge piece of understanding. Now, DOE, I'm not sure I have an answer to you, Varun, because there's no one right way to do it. And obviously you'll do things that you have found to be successful in your career. For me, DOE is you have a model in mind and you want to go investigate that model for understanding of potential causal relationships. Stepwise is an approach you take when you don't have a model in mind. And so this is why, as Victor said, that's a data mining approach. So that's not really your go-to for analysis of DOE. Now, you should go into the DSD going, here are the effects I'm suspicious of. There's the main effects you're suspicious of. Certainly the DSD offers the option of estimating nonlinear effects, which your typical screening designs do not do because they're typically two-level designs. However, you go into it with some kind of model in mind. Even though you're screening, here are the factors, here are suspicious second order linear effects, here are suspected second order nonlinear effects. And that's what we're testing with the DSD. So DOE is, I go in with a model in mind, and then I use the data to help determine and refine that model. Whether that model suggests we need to move the space or augment in place, we have to wait to see the data to help us make those decisions and so forth. So there's no one right way to do it, but stepwise is not the typical approach for analysis of an experiment. I don't know if that answers your question, but by the way, in this data set, you got to realize these p-values are so strongly significant because there's very little estimate of the random errors. Basically, the random errors are estimated by the degrees of freedom of the replicated center points, where all the factors are zero. So just by the way, for discipline, a data table for DOE, you have to have run order in there. I don't know if these center points were run 4 in a row, which would be very different than if they were randomly run throughout the course of the experiment, which will give different estimates of the random errors. But there's a small estimate of random error, which is likely to inflate p-values. So you got to be very careful of using p-values to make those statistical assessments. Richter did show. JMP does this quite well, by the way. The model, the two-factor screening model, where it gives a Daniel plot, which is a normal plot. That's a great plot because it's unbiased. It doesn't have a biased mean square error estimate, and therefore you're really just comparing relative magnitudes of each of the effects in the models. That's my go-to for analysis of these screening type designs, because it's so hard to get an appropriate estimate of the mean square error often in these screening design spaces. So for more information on that, you should read Daniel and why he invented Daniel plots to do that. But yes, but I will say this. If you've been successful doing your stepwise analysis of DOE, I'm not here to say don't do that. I'm just saying that's just not. But first of all, that wouldn't be my approach. It doesn't mean my approach is right, by the way.
Yeah, no, thanks, Bill. I usually don't use the DSD. I have background expertise. I always do custom DOEs, and then I don't use stepwise, but this is in my career I have started using DSD because number of factors have exploded in certain applications. So that's a new era for me, but thanks for all the feedback. I think that would be helpful.
Do realize that DSDs do confound second order linear and second order nonlinear. They're not completely, there is correlation between those second orders. So just be aware of that.
So we are 2 minutes to go. Ole, I see your hand raising, but Simon, we haven't forgotten about you, so maybe we have time to do both. Ole, is this going along the discussion?
Yes, it's the same. I just wondered, I'm aware that there are some factors which are correlated with each other. Is there a simple way in JMP to define that I have some factors which I do not want to correlate with each other because I think that these interaction terms most likely play a role, and by other ones I might know that they usually don't play a role? So I know, of course, from custom design, but is it in the DSD possible kind of to say these are the factors I would like to separate?
Does anybody know that?
Yeah, I don't know that DSD is considering specific second orders from specific second order nonlinear. I don't think that was the idea behind the development of the method. I mean, no doubt the development of the method was, as engineers or scientists, we certainly don't believe there are truly linear effects anywhere. I mean, there's really no such thing as straight lines in space. So we know this curve. The question is the curvature, is what I call the departure from linear, great enough to warrant investigation, or is the linear approximation sufficient? And so DSD offers, well, since we already don't believe there are perfect linear relationships, let's at least get estimates of that departure from linear when we're doing screening. Because as Victor points out, if you pick level setting that are extreme and optimum is inside, and that departure from linear is quite large, then the potential to drop the factor, this is the beta error, drop the factor and don't investigate it further is a mistake. And so like Bill Diamond would say, well, don't put your levels so far apart. And so there's different approaches to, trying to get that linear approximation to be more true. But that's why DSD came about, was just to investigate, I'll say more thoroughly, the nonlinear. I mean, of course, the other option is to do two-level designs and add center points. It confounds all the second order nonlinear effects, but it is like a test of linearity in your design space. So that's also a potentially good option. Again, keep in mind, while DSD allows for categorical factors, that's really not the forte. It's really for continuous factors. So if you're dealing with categorical factors in the screening phase, the two-level and the linear approximation is a great way to start. Yeah, that's all I'm going to say in the 20,000 experiments I've run.